All right, it's 10:20. So I've started the recording. So if you're on, recognize I am recording this, so you will be heard. But I want to say welcome. And it is a matter of, I hope the test was pleasant and more for some than others, I'm sure, but I hope it went well for you. And several of you got done pretty quickly. That was pretty cool. In the amount of time it took you to take the test, I saw that, but trusting that things went well. Okay, well, one of the things I want to say, I went in and updated gradebook a little bit. It had been a little off kilter, and the numbers were, I was double dipping sometimes, and that meant the numbers were a little bit larger than the total possible. Right now, if you look in gradebook, though, the total number of points you have, it's out of 200 possible. We were at an even 200 right now between in-class problems, quizzes, exams. Oh yeah, well, 200, not including exam 2. So if you look right now, you've got your grade. It's got everything in there. There's, again, a couple of you that had extra credit points. You went over, I'm not extra credit, but you got more than 20 on that last quiz, and that wasn't included. So add that in if you know that you got that and it wasn't included. But that is done, and I want to remind you that and the scores it'll be pretty close to what the actual value is of what your score is out of 200. So you can check that out, verify what's going on. Several of you are doing well, and it's very positive. And some of you I've noticed by going through the when I went through the sapling problems, discount setups, there's a couple of you that backed off a little bit, a little prematurely. A couple of you stopped doing the problems and you got less than 20 as a result. I mean, it was really close. Let's see, 5, 8, 12, 14, 17 of you got 20. And another 1, 2, 3, 4 of you got over 18. So it is a matter of, you're doing the problems. It's fantastic. You're doing it well. And if you've got questions on anything, make sure you let me know. But if you stop short, a couple of you fell a little bit short of getting them all done, and you had zeros in a couple places. So you could still go back. Something you did not do any problems in, go back and get 70% still and add that to your total. That could bring it up over 20. If you got less than 20 under the column that has to do with sapling problems, SE2, I think. That's what I got it called. Should be worth 20. If you got less than that, make sure you check it out and see if you can boost that up a little bit. All right, what I want to talk about today, like I said, I'm going to step back just for a second into section 3.3 and talk about something that's going to be included in the semester here. Calc 2 is where it's used significantly, and it's just a matter of getting some algebraic skills down too in the process of working with it. So what I want to do right now is go to the, I want to look at my screen that has me going for this one right here. Okay, and it's got to do with, let me get the slideshow, current slide. Okay, so it's the derivative of the inverse sine function, all right? So remember this, all right? This is something I want to get across is that remember, the inverse sine is something which the angle whose sine is some value. Y, and this what I've got shown here is y is actually the angle whose sine is x. So the x value goes here, and you get the circumstance there. And I want to show you how they came up with the formula. It turns out this is something that I will give you on the formula sheet. But the end result is that the inverse sine function, the derivative of the inverse sine function, ends up being this. And I want to show you the math of how they did that. There's only going to be a couple of them I'm really going to work with this semester. I'll work with inverse sine and inverse tan. And inverse tan I won't even really go through because it's a similar process as this, using trig identities and a combination of different things to get the solution. And I'm not going to ask you to do this, but I just want you to show you where it came from. The idea is this. If the inverse sine function is y, then remember what that means. to get rid of that minus, I could rewrite this as getting rid of this minus sign. And it would be the sine of y equals x. Okay, if I switch these letters, then it would be switching it. The inverse sign means you're switching the variables, and that's one way to look at that. So the situation would be that if I say the sine of y equals x, then we're again manipulating something so we can get some information. So I can take the derivative of inverse sine and get a function that works for it in terms of x. Okay. So if I start with sine y equals x, and now take the derivative of this, derivative with respect to x of each side. Okay, so I've got the derivative with respect to x of each side here. All right. And because there's a y here that's a function in terms of x, that means I got to use the chain rule on this side. And as a result, this is where the dy dx is going to show up that we're solving for. So if I take the derivative of this side with respect to x, I get the derivative of the outside, derivative of sine is cos of y, stays just like it is, the inside the parentheses type thing. And then I've got to take the derivative of y with respect to x, which is dy dx. So here's one equation, and then this arrow is saying this is not an equal sign. Notice you don't keep an equation equal to another equal sign, another equation. So this arrow is indicating now the new equation is, so the derivative of cosine is cos, and then you got cos dy dx, and the derivative of x is 1. And then the result is, here's my new equation. I've got cosine y equals this, and solving for dy dx, divide by cosine y, I end up with dy dx equals 1 over cos. All right? So that's the situation, and now we manipulate, do a trig identity situation, plug it in, and get the thing to have x in it instead. So remember, anytime you've got a situation, cosine squared plus sine squared equals 1. Sine squared plus cosine squared equals 1. So, and they did that in terms of y also here. So if you had sine squared plus cosine squared equals 1, subtract sine squared, and you get cosine squared equals this, 1 minus sine squared, and then the arrow gives you the new equation. If you take the square root of each side, you get cos equals the square root of 1 minus sine squared. Okay, the logic of that situation. I think you can see the algebra of that. And then remember that x sine y, this is really sine y squared, that's what that's saying. Sine y is x. So if you place sine y with x, you get x squared. So you end up with what we started with, derivative of inverse function, inverse trig function, sine. So the derivative of the inverse sine function is equal to 1 over the square root of 1 minus x squared. In the future, like in Calc 2, there's going to be different circumstances, equations that you'll be presented that look in this format. And when you can work with this in this format, you can do an antiderivative and get some benefit, a function that you can talk about and do some work with. Okay? So this is one of the key situations that I want to talk about. Let's do an example of what that means. So if I give you, this is what I'm going to ask you to be able to do. So if I give you, I'm going to give you the formula, what the derivative is, but find y prime if y equals inverse sine function of 5x cubed. So the original function is this. Here's the derivative of a function. All right? Got to remember, this is not just x. So that means we got to use the chain rule. When we take the derivative of this, we got to use the chain rule because this is not just x. All right? So that's something you got to notice right from the beginning. I'm going to use this rule. This is my u, we're saying. So u is going to go here. 1 minus this squared, square root. And then I got to remember to take the derivative of this. All right? So as an end result, we've got the original function times the derivative of the inside function gives us 1 over this, the 5x cubed goes in here, squared, right? So that's going to be 5 squared, and x cubed squared, which gives us x to the 6th. That's 5x cubed, I mean, it's 5x cubed squared here times the derivative of this, which is 15x squared. So it turns out that goes on top, this gets substituted in, and the final answer is given right there, okay? Don't be distracted by that 25 and you got a square root. This is connected by that minus sign, so you can't factor this. This whole thing has to be a factor in order to take the square root of it. Remember that, okay? So that's a type of a situation we'll be given. I'm also considering using the inverse tan function. It's a little bit different. It's a slight variation. Cosine is real similar to sine, but if you look at inverse tan, notice there's no radical in the bottom this time. You use a different trig function, and the derivative of inverse tan is 1 over 1 plus x squared. Okay, that's tan. Cosine, notice, is the same as inverse sine, except it's got a minus sign out front. Okay, but sine, cosine, tangent, I'm not even going to do cos. Just sine and tangent, inverse sine and inverse tangent functions are what I'm going to ask you to work with. There's a couple others for secant and cotangent and cosecant, but I'm not going to worry about that right now. I want you to get the gist that those are out there, and when you get the Calc 2, you'll be able to use these in a more clear way. So I'll include this in something coming soon, okay? So let me see the next, okay, that's basically what we want there. That's all I wanted. The next thing I want to do is I want to go to section 4.2. I said I was going to jump to section 4.2. So what I want to do is go then to 4.2, which is this puppy right here. Yeah. Okay, so 4.2. Let me get that on large screen. Okay, so 4.2, the section is regarding maximum and minimum values and critical numbers. Those are some key terms that we're going to be talking about. And some of this stuff is matter of fact. What's the maximum value the function ever gets? Okay, what's the minimum value the function ever gets? That's called absolute. And that's what we're referring to. And also there's local extreme values. So they called extreme values if you talk about max and min. So if you're ever asked the local extrema or something like that, that's talking about what are the maxes and mins for the interval or for the entire function or something. That's something to consider. And then also we're going to define critical numbers, and that's going to be a key part of several of the problems that I'm asking you to do in section 4.2. Like I said, there's 19 of them. So once you get going on them, do it. You know, don't wait, because there's going to be more coming for the future stuff. By the weekend, I really would like you to have those done, or you can finish them over the weekend, but get cranking on them and come up with questions that you can ask and clarify. Some algebraic situations do show up, but I do want you to get familiar with the thing. So the definition of absolute extrema, that's the word I was talking about, extrema, meaning maxes and mins. All right. And the absolute max and absolute min on some interval, okay? In I is some interval, on an interval I. It might be the entire function. It might be the entire function, but the idea is that what your circumstance is that you're wanting to find out what the max and min are on that interval. It might be, again, the entire function. But the circumstance is, the definition of absolute extrema, absolute, is meaning on the entire, whatever region is you're talking about, the highest value is the absolute max, and the lowest value is the absolute min. All right? And that's the situation. Sometimes it's going to be on the entire function, like I said. But sometimes it's going to be on an interval from 1 to 3, say. You know, what's the highest this function ever gets between 1 and 3? Absolute means the highest it ever gets. We're going to also talk about local, which means something a little differently. And I'll talk about that in just a second. Absolute values, absolute max and absolute min are that it's higher than any other value in the function, or it's lower than any other value in the function if it's absolute min. Okay? So this diagram is an example of it. So if this is interval, notice it stops here. There's no dot drawn there, but they're stopping it here. So the interval's going from A to B, all right? And they put the endpoints so that they aren't, so the lowest point is visible. There is a lowest point in this situation. It's right there. That will be the absolute min. And the absolute min value, notice, is the value of the function. The minimum means how high is it up and down. Down, it means it's the y value. The x value is where it happens. But the y value is the absolute min here. The absolute max on the interval, the highest on this interval between A and B, the highest it ever gets, the absolute max is at f of u. It's at x equals u, okay? This is where it happens. But the actual value is the y value here. We'll talk about that more. So this is on a situation where, notice this, if this went down forever and this went up forever, then there would be no absolute min because this goes down further and it's going down forever. So if you did the entire interval on this entire function, then there wouldn't be an absolute min or an absolute max, but because this is limited to going from A to B, not including A and B, notice, that's an important part to pay attention to when we talk about some details here. But the absolute max happens here, and the absolute min happens here, and they are the y value at those points, okay? So let's go on. I want to show you this. Now there's another scenario where it's called a local max or local min, which means the area immediately around it. The area immediately around it, all the values really close to it, this is the highest point, okay? Or the lowest point. This is the highest or lowest point. And this is going to be a real important thing to say on this, okay? This detail. It's an open interval, I, okay? It's got to be an open interval. So that means there isn't the endpoint on that interval. It needs to be on an open interval is what we're talking about for relative max and relative min. And those are called local extrema. Relative, meaning relative to its immediate surroundings. Local, it's right in the neighborhood, okay? So the word local or relative is talking about not absolute. Absolute means on the entire function. Local or relative means in the immediate area, okay? So, and local is also on a open interval. Always, open interval is what we're talking about here, okay? So let's look at this example. So, is there a highest point for the entire interval? Yes, there is. There is a highest point. That is an absolute max, okay? That's the absolute max of that function. Absolute max is f of whatever the y value is the maximum value the function ever gets. Now this would be considered a relative max. It's not an absolute max, but it is relatively max because it's local max because everything right around it, it's the highest point. All right. Notice also, this is the notation. If we picked an open interval around here, this also would be considered a local max, okay? Because in the local area immediately around it, it is the highest point. So there's a local max. Here's a local max. But if you're asking absolute max, this is not an absolute max because there's a higher point somewhere in the interval between A and B that we're considering. So here's an absolute max. This is a local max, a relative max. And this would be, because there are lower values, this is a min, but it's a relative min. Right around it, this is the lowest point. So this is a relative min. And these would both be considered, if it stopped at A and stopped at B, notice there's no dot there. If it stopped there and there was a dot, this would be an absolute min. Both of these would be absolute mins. But there is no dot there. So do you ever get to the bottom of the thing? No, this would be a situation. Even though there's you stop the mark somewhere, there isn't a smallest value, because you can always get closer and closer and closer to y equals 0. So there isn't, in this case, a relative min. Relative max, boom, boom. Absolute max, yes. And relative min happens here. Relative min happens here, but there is no absolute min in this case, all right? If I said relative min to go down here, I meant to say these are both absolute, not, these are not absolute mins. This is not an absolute min because there's places lower. But this is a relative min. These are not relative mins. Okay? We'll keep doing more problems and we'll get familiar with it. So look at this situation. Here's an example. Identify, you'll be asked, what's the domain? Where is it continuous? Is there an absolute max and min? Those are kind of questions you're going to be asked on several problems that I'm asking you to do in section 4.2 and in 4.4. But the local max and min, are there absolutes? Are there locals? Let's find out. So the domain, what is the domain of -4, 2? What values of x happen? Okay. In this diagram, the domain is from -4 to +2. Every value of x happens. Okay. It's got an answer. Even though this doesn't, never quite gets there, the limit is there, but the limit's here, but it's defined here. But every value you do a vertical line test, it passes, it's a function, and every place gets hit at least once. So the domain is -4 to 2. Is it continuous? It's continuous on the whole thing, except at where this is a jump discontinuity. So it's continuous. Is it continuous? Where is it continuous? It's continuous everywhere except at x equals 2. Good answer. Is there an absolute max in this situation? Look, the highest this gets is here. There are values that are higher, and this never gets there. So there is no absolute max. Is there an absolute min? Yes. This one has a bottom here, but there is a lower one down here. So the situation is that that the absolute min happens here at 0, 0. Now they said something inconsistent here, inconsistent with the book. They say there's a local max here, but it needs to be on an open interval. We need to talk about that some more. The book says open interval. This is not an open interval, And if you have an open interval that goes to 2, that point is not included. So this is a little inconsistent with what they said earlier in that definition. We'll talk about that again. To me, it made sense to me that this could be a relative max because there's something higher. But by definition, they were saying on an open interval. So I'll clarify that a little bit more. They threw me off just here with this slide. We'll talk about that a little bit more downstream. By the definition they give in the book, this does not have a relative max, okay? It doesn't have the local max doesn't happen here because there's no max. They're saying it does here. By that definition, this is not an open interval. So I question that. Well, and I'll clarify that on any assessment. We'll make sure it's clear. But the absolute max, there is none. Absolute min, there is one, absolutely. Relative max, by the definition they're saying, the local max, but I hear what they're saying, there is something higher. This is a max in the area right around it, not to the right side though. So the open interval situation, there's a problem there. So we'll talk about that again. I'll clarify that tomorrow and make sure we're solid on what we're going to say about that. But this is inconsistent with what they give in the dictionary definition, okay? So we'll clarify that. All right, so let's look at this now. Identify max and min. Domain, look at the domain. What values does x take there? Open on this end, closed on this end. It goes from -6 to 9. And open at -6 doesn't happen, but at 9 it does. X equals 9. Continuous on the entire interval. Is there an absolute max? This is not absolute because there's higher. This is an absolute max. Yes, absolute max is 10 at x equals 9. This is another way of saying it. Absolute min. Is there an absolute min? Is there a lowest point on this entire function? Yes, there is. Here's open at 6 and negative. They're both at 1.3 on y, but this one happens, this one doesn't. So the absolute min does happen here. Local max happens here. Local because there's nothing close around it. And again, they're not being a bit consistent here, but yeah, okay. So local, they don't call this a local max, notice. That's consistent with what their definition is. But local min, they also say this is a local min, and that's not, if it's the open interval, there is the local interval, the local min. They say local min at 0.8. That's a local max. They mean local max. And they mean local min here. Boy, they've got typos on this one. Local min is here. All right? Local min here. Local max here. And we'll talk about if this is a local max or not. Okay? So according to the book, the definition they give in the book, this is not a local max. Typos on their part here abundant. I'm sorry about that. Let's go on to the next. Now, the extreme value theorem says this. If f is a continuous function on a closed interval, then f has an absolute max and it's got an absolute min. It's got to have. If it ends to the right and to the left, then it's got to have an absolute highest and an absolute lowest value. It's got to happen. Okay, that's the extreme value theorem. That's kind of, it's called an existence theorem. It says if you've got a function that's continuous between a and b, then the max exists. The absolute max and absolute min exist, right? And the condition for local max min, notice this now, condition for local max or local min, if function f has a local max or local min, then either the slope, the derivative is 0, the slope is 0, or it doesn't exist. See, this has a local max, but the slope doesn't exist here because it's got a cusp going on, okay? So this does not exist, but there is a local max here because to the right and to the left, it's the highest point, all right? And to this one, local max, local min, because it's the lowest point, it's got something on either side, all right? So now here's a key point that you're going to be working with in section 4.2. A lot of it is find the critical numbers. What's a critical number? Okay, well, the critical number of a function f is the number c in the domain for which either the derivative of that x is equal to 0, the slope is equal to 0, or the slope does not exist. So where the slope is 0, that's a critical number. If the slope does not exist, that's a critical number. So if you're asked for the critical numbers, find out where the slope is 0 or where the slope does not exist, and those are the answers. So here's an example of it. So it says find any critical numbers of this function. This is a polynomial, and that's going to be a straightforward one, and I'm going to try to keep to this pretty strongly through the beginning part of getting through the beginning stuff, or the quiz and stuff on Monday. But since f is a polynomial, some of the problems on sapling are not this simple, okay? So I'm going to ask you to dig in and try the algebraic aspect and make sure your algebra is cool on the sapling stuff, but I'm going to basically make sure you understand this concept right here, the way it's presented here. Find all critical numbers. So f is a polynomial, differentiable at every real number. It's a polynomial. So the critical numbers are the place where the slope is equal to 0. It's defined everywhere, so where's the slope equal to 0? Take the derivative. Derivative of x cubed is 3x squared minus 12x minus 12x. plus 9. Got it. Okay. Factor it. You're finding where this equals to 0. So take the derivative, factor it, set it equal to 0, find out what numbers cause it to be equal to 0. So the answer is take the derivative, set it equal to 0. That's what you're doing. Take the derivative, factor now. This is going to be take your factoring skills. Remember, if you factor the 3 out here, you end up with x squared minus 4x plus 3 plus 3 minus 3x minus 1x gives us minus 4x. All right. And what I want to do is to verify the situation that, so the derivative is 0 when we set this equal to 0 now. That means x minus 1 equals 0, x equals 1, x minus 3 equals 0, x equals 3. All right? So the numbers 1 and 3 are critical numbers. Those are the critical numbers. If you're asked to find the critical numbers, take the derivative, set it equal to 0, factor it, set it equal to 0, and find the values that cause it to be equal to 0. All right? That's that. The critical numbers are 1 and 3 for this problem. So let's take a look at this. Is a little more complicated. I'm not going to worry about that right now. One other thing I want to point to, though, is this. So step for finding absolute extrema. And you're going to be asked to do this in the problem. Find the absolute max and absolute min in section 4.2. And notice, given a function f that's continuous on a closed interval, locate all critical. So the first step is find the critical numbers. Take the derivative, set it equal to 0, and see if there's any place it's undefined. And if it's undefined there, you can't take the derivative, then that's a critical number also. But then the idea is you've got the situation of A and B. You've got A and B are your outer limits of this situation. Find all critical numbers. And then what you got to do is it could be that the situation is going to be that going off to the right, the highest point is going to end up being at the end point, at B. It's going up as it goes off, but it ends at B. So the highest point could happen at B. And the lowest point could happen at B, but the low could, I'm going to do an example in a second to make this clear, but the lowest to the left, for instance, could be at A. The lowest to the right could be B, and you can have zeros in the middle. That's going to be a very common feature, but every time you got to check the endpoints to see if it's a high or a low. So it says, what you're going to do is locate all the critical numbers, where's the derivative equal to 0 or undefined, and then plug each of those critical numbers into the function and find out what, and then the largest value is the absolute max, and the lowest value is the absolute min. That's it. That's it. So find the critical numbers, what causes the derivative to be equal to 0, or where is it undefined, and where is the derivative undefined, and then evaluate f at all the critical numbers and at the endpoints. So you got to check, because sometimes it could be going off to the right, to the left. The largest is the absolute max, the smallest is the absolute min. So here's an example. Find the absolute max and min of this function. And what I'm going to do is I'm going to move this over